In this lecture, we're going to learn a set of ADMM type methods. In this lecture, we will cover FLiP-ADMM, which is a general and highly versatile variant of ADMM. We're going to present its convergence analysis, and we'll derive a wide range of ADMM type methods from FLiP-ADMM. Finally, we further generalize it to a method we call TRIP-ADMM. Let's start with FLiP-ADMM method, main theorem, and discussions. FLiP-ADMM stands for Function Linearized Proximal ADMM, or Alternating Direction Method of Multipliers. It solves the problem where we minimize f of x plus g of y. Subject to ax plus by equals c, when we further divide f into f1 plus f2, g into g1 plus g2, this is a typo, it should be g of y. And we assume all these functions are CCP and f2 and g2 are differentiable. Here we write down its Lagrangian. To present the method, we choose scalars rho and phi and symmetric matrices P and Q that are positive semi-definite. FLiP-ADMM is a three-step method. It updates x, then y, and then u, and loop like this. When it updates x, it minimizes f1 of x, the inner product of x with the gradient of f2 at xk, and dual variable multiplied to A transpose, plus the penalty term, plus the and proximity term induced by matrix P. Similarly, when we update y, we minimize g1 of y and use the gradient of g2 at yk, the UK term, the penalty term, and the proximity term induced by matrix Q. And when we update U, not only do we multiply rho with the constraint violation, we also add an extra scalar phi there. If we set f2, g2 to 0, therefore have the two gradient terms vanish, P and Q matrices as 0, therefore have the proximity term vanish, and set rho equals 1, then we recover the classic ADMM. Theorem 6 is the central theorem of this lecture. It gives a set of conditions under which FLiP-ADMM iterates xk and yk such that the objective sequence converges to the optimal objective and the constraint violation sequence converges to 0. The set of the conditions include total duality, that both x and y subproblems have solutions, f2 is LF smooth, g2 is LG smooth, and there exists a scalar between 0 and 2 minus phi such that these inequalities are satisfied. To clarify, this inequality means that P minus L sub f identity is symmetric positive semi-definite, and this matrix minus 3LGI is symmetric positive semi-definite. And we will look at these conditions next. Let's look at this last inequality constraints in the theorem. It imposes restrictions on phi and rho. If we set the scalar phi to square root of 5 plus 1 over 2, which is the golden ratio, then this term equals 0. And from this, it's easy to deduce that if phi is between 0 and the golden ratio strictly, then there exists a small positive epsilon such that this term, which is inside the parentheses, is positive. Therefore, a larger rho helps us satisfy this inequality. If rho is above golden ratio and less than 2, then there exists, and for any epsilon in this range, then this parentheses is negative. Therefore, smaller rho will help this inequality to get satisfied. In FLiP-ADMM, matrices A and B are given as part of the problem. Constants L sub f and L sub g are given once f2 and g2 are specified. The rest of the constants, such as P matrix and Q matrix, scalars rho and phi, are subject to our choice. These choices not only determine whether they satisfy the sufficient conditions for convergence, but they actually also affects the convergence speed and the cost per iteration. The optimal choice for a given problem balances the speed and the cost. Next, let's discuss the parameter choices, the special cases, and differences. Let's look at golden ratio ADMM, which is generalization of classic ADMM with the extra dual extrapolation parameter phi. Setting phi greater than 1 may provide a speed up. And if we set f2 and g2 equal to 0, p and q to 0, such that the proximity terms vanish, then FLiP-ADMM reduces to golden ratio ADMM. Using augmented Lagrangian L sub rho, we write the standard ADMM updates on x and y as such. The only difference from standard ADMM or classic ADMM is this additional dual extrapolation parameter phi. Theorem 6 guarantees that this method converges when phi lies between 0 and square root of 2 plus 1 over 2, which is approximately the golden ratio. Next, let's look at the penalty parameter rho. Rho controls the relative priority between the primal and dual convergence. Indeed, in the proof below, you will see the upload function contain a primal error term and a dual error term. And the primal error term will have a factor rho, and dual error term will have factor 1 over rho. A larger rho prioritizes primal accuracy, which means this term without rho tends to reduces faster. And a smaller rho prioritizes the dual accuracy, which means this term without the factors in front of it tend to reduces faster. Next, let's look at the proximity terms induced by P and Q, which appear in the X subproblem and Y subproblem. The letter P in FLiP-ADMM describes their presence. Empirically, smaller P and Q lead to fewer required iterations. When f2 equals 0 and g2 equals to 0, we will be allowed to choose p equal to 0 and q equal to 0 to satisfy the conditions of the theorem. And these are smallest possible choices of p and q, therefore, they're optimal in the number of required iterations compared to setting a positive definite p and positive definite q. However, proper choices in p and q can also cancel out certain computationally awkward quadratic terms, and therefore reduce the cost of subproblems at each iteration. So later on, we will present an example where we will choose such a p and q. FLiP-ADMM uses the linearizations of the functions f2 and g2. Recall they are differentiable. Here is the equivalent rewriting of the X subproblem of FLiP-ADMM. Compared to the original form in FLiP-ADMM, we have added the terms that are independent of the variable x into the subproblem objective function. Therefore, it does not change the subproblem. It does not change the way argument works. So the added terms are f2 of xk, the inner product of this with xk, g of yk, inner product between uk and byk minus c. Writing the subproblem this way, we can see that we have replaced f2 of x by its linearization, which is f2 evaluated xk plus this inner product term. We call it linearization because this function is linear in x, and this one equals f2 at the point xk. So this is described by FLI, or function linearized, as in FLiP-ADMM. When we apply FLiP-ADMM, we have the choice to use f2 or not. Choosing f2 equals 0 tends to give you fewer total number of iterations. However, non-zero f2 reduces the cost of the subproblem because we only need to calculate the gradient at xk. And f2 is not involved in minimization. This is the discussion on f2 or the x subproblem. The same discussion also holds for g2 and the y subproblem. The letters MM in FLiP-ADMM stands for the method of multipliers, which refers to the problem with only one primal subproblem with all just the x but no y. If we set q equals 0, then the entire y subproblem, including the B matrix, the Q matrix, and G1, G2 all vanish. Therefore, FLiP-ADMM reduces to the method of multipliers, except we have this extra constant, a dual extrapolation parameter phi. According to theorem 6, this method with this phi will converge for phi between 0 and 2. Now we proceed to discussing the proof of the main theorem. Theorem 6 is very different from the theorems from previous lectures. Theorem 6 establishes the convergence of the objective values, which are the f of xk plus g of yk, and also establishes the convergence of constraint violations, which are matrix A times xk plus matrix B times yk minus vector c. Theorem 6 does not establish the convergence of the iterates. And the convergence proof we present below does not rely on the machinery of monotone operators. The main challenge of the proof is to construct an appropriate Near-plot function, which is a name or term borrowed from nonlinear systems used to prove the system stability. The proof is not very long, it only takes about 4 pages in the textbook. It's relatively easy to follow. It's easy to verify. However, the construction of the Near-plot function and some of the inequalities are not intuitive. This is because ADMM type methods are modular. The classic ADMM is the simplest form. The proof comes from the insights that we have accumulated over the years of reading and writing papers on various different kinds of ADMM type methods, from simple to more complicated ones. Let us define the constants and the Near-plot function used in the proof. Recall we assume total duality, which means the Lagrangian L has a saddle point x star, y star, u star, and concatenate them into vector w star, and also concatenate the iterates xk, yk, uk into wk. Define a constant eta, and define 3 block diagonal matrices. The off-diagonal entries are all 0, and the assumed conditions of the theorem guarantee that the matrices on the diagonal are all positive semi-definite. Therefore, we can use them to induce semi-norms. And define the Near-plot function as wk minus w star norm induced by m0 squared plus wk minus 1 norm induced by matrix M1 squared, and we will use matrix M2 later. To clarify, this norm is the sum of the norm between x star and xk induced by half time p, and the norm of y star minus yk induced by half times this matrix, plus the norm of u star minus uk induced by this matrix with half in front of it. So there are really 3 terms here and another 3 terms there. Using these concatenations and the block diagonal matrices allow us to write the proof and the Near-plot function in a concise way. At this stage, these choices don't explain by themselves. They actually come out of the proof. Let's start the proof. We will present the overall flow of the proof in 4 stages, and we discuss what to achieve in each of the 4 stages. However, in the lecture, we will not explain how to obtain every inequality, so for you to verify or to understand the whole proof, you must read those 4 pages in the book. The proof begins with the fact that xk plus 1 and yk plus 1 are subproblem minimizers. Using the optimality conditions of subproblem minimizers, we can write out 2 inequalities, one that relates xk plus 1 to x star, and the other relates yk plus 1 to y star. The one relates xk plus 1 to x star will involve functions f1 and f2, matrix A and matrix P, similar for the other one. Adding the two inequalities and use definitions of Lagrangian L and definition of update UK plus 1, you can write down this inequality where the left-hand side is non-negative due to the definition of Lagrange, and the right-hand side includes 4 squared terms and 2 inner product terms. To clarify, the first inner product term is induced by the diagonal matrix M0. So that really it expands into 3 individual inner product terms, one involving x vectors, and the second one is involving the y vectors, the last one involving the u vectors. Recall from previous lectures that in the proofs we always come up with non-negative terms to draw conclusions on. However, given the information so far, we're not able to determine the signs of these two inequality terms yet. Therefore, we need to further transform and decompose them. We first bound the second inner product on the last slide. Notice that there are yk plus 1 and yk in this inner product. So we can use the fact that yk and yk plus 1 are the y subproblem minimizers at the k minus 1th and the kth iterations. And they give two inequalities, and add those two inequalities, we can obtain this new inequality, where the left-hand side is inner product, and the right-hand side is its bound. And this bound involves 3 quadratic terms, including 1 negative quadratic term, as well as 2 new inner products. At this point, we simply apply Young's inequality to relax these inner products. And Young's inequality states that the inner product of 2 vectors A and B can be bounded by their individual norms with proper weights. Here, these weights involve a scalar zeta that is any number positive. If zeta is taken as 1, then this reduces to the Cauchy-Schwarz inequality. When you apply Young's inequality to a Q matrix induced inner product, you simply get on the right hand side the Q matrix induced norms. And when you apply it with the negative sign in front of the inner product, you still get the same right hand side because the right hand side is always non-negative. When we apply this Young's inequality to these two inner products, and we choose different zetas for these two terms. Apply Young's inequality to the 2 new inner product terms on the right-hand side, allow us to get the new right-hand side. And we have used this induced norm notation to collect the terms. So we end up having only 3 terms, one involving yk plus 1 minus yk, the second yk minus 1, and the last one uk minus 1. The second term is non-negative because the matrix is positive semi-definite. The last term is also non-negative. However, the first term is undecided because it's unclear whether this matrix is positive semi-definite or not. If it is negative definite and yk plus 1 is different from yk, then this term is actually negative. We write it like this only to save space. There are other yk plus 1 minus yk norm terms with different matrix, and they're going to combine, all of them going to combine. We only need to ensure that the matrix as induced norm for yk plus 1 minus yk in the Neapola function to be positive semi-definite. So we were applying Young's inequality to the 2 new inner product terms on the last slide. You may wonder, what if we directly apply Young's inequality to this left-hand side term rather than taking 2 slides to taking these steps to get this bound? Well, if you do that, then we will not able to obtain terms of yk minus 1 and this term. So these two terms will not be obtainable. And this will not allow us to include these terms in the case Linear function, and which also mean any yk plus 1 minus yk terms have to be absorbed not by the Linear function but by another means, which we will not able to do. Recall in stage 1 we ended up getting 2 inner product terms to handle. In stage 2 we have bounded the second inner product term, and this is the remaining inner product term, and it can be handled by this generalized cosine identity. So add all add this identity, the bound from stage 2 to the bound in stage 1, we end up getting this master descent inequality, which states that the case plus 1's Linear term is less than or equal to the case Linear term subtract this amount. So this is the amount that the Linear function has to decrease minimally at the case iteration. This term is non-negative because M2 is block diagonal and positive semi-definite, and we have argued that this Lagrangian difference term is also non-negative. Recall that the Linear function formulation involved two squared terms involving two positive semi-definite matrices. So the Linear function is lower bounded by 0. It's always non-negative. So this descent inequality immediately means that this term have to converge to 0 as k goes to infinity, as well as this term. So applying the summability argument on the master inequality tells us these two conclusions. The wk plus 1 minus wk norm term converges to 0, and this one decomposes to 3 induced norms, and the last one is the induced norm of uk plus 1 minus uk. So it actually tells you uk plus 1 minus uk converges to 0. And looking at the formula for uk plus 1, this is just a scaled version of the constraint violation. So the constraint violation must also converge to 0. Looking at the second conclusion, and we expand the first Lagrangian term to f and g evaluated at their respective points plus this inner product. And this one is equal to f of x star plus g of y star plus 0, because in the inner product term, the constraint violation is actually 0 because everything's optimal. So this difference converges to 0 really means f of xk plus g of yk converges to the optimal objective. So these are the two conclusions we have in the theorem.